NASA has confirmed that interstellar object 3I Atlas is not natural at all, but made of industrial material. Now scientists are scrambling for answers.
An ancient space rock from another star system just did something that has scientists completely baffled. After hiding behind the sun, the interstellar visitor 3I Atlas emerged glowing much brighter than predicted. This thing survived 7 billion years traveling through the galaxy. But now it's acting so weird that the United Nations activated planetary defense protocols for the first time ever. Is this just a strange comet, or could we be looking at something far more extraordinary? The mysterious space visitor that has scientists worried. Something absolutely incredible happened on October 29th, 2025. While most people were going about their normal day, telescopes around the world were all pointed at the same spot in space. An ancient visitor from another star system was making its closest pass by our sun. But what happened next has left scientists scrambling for answers and has triggered something that has never happened before in human history. The interstellar object called 3I Atlas came back from behind the sun, and it was glowing much brighter than anyone expected. Not just a little brighter, but dramatically brighter in ways that make no sense according to everything we know about how these space rocks should behave. The brightness spike happened fast, twice as fast as the weeks before, and it caught everyone off guard. This isn't just any random chunk of ice floating through space. This thing has been traveling through the galaxy for somewhere between 7 and 12 billion years. That means it existed before our sun was even born. It's 3 times older than Earth itself. Think about what that means for a second. This object has survived every radiation blast, every gravitational pull, and every cosmic collision for longer than our entire solar system has existed. But now, it shows up here and starts acting in ways that don't match any of our computer models. The people watching this happen, like Tongjiang at LOL Observatory and Carl Bams at the Naval Research Laboratory, are seeing numbers that just don't add up. When they break down the light coming from 3I Atlas, they're finding something that changes everything we thought we knew about visitors from other star systems. An ancient traveler's billion-year journey. To understand why scientists are so puzzled, you need to know what 3I Atlas went through to get here. This object has been floating through the emptiness between stars for billions of years. During that incredible journey, it passed by other stars, traveled through radiation fields that would kill anything living, and survived gravitational forces that could tear apart weaker objects. Every step of that journey left its mark. Cosmic rays from exploding stars have been hitting 3I Atlas for eons, going deep into its surface and changing its basic structure. According to Roma Maggiolo, who studied this at the Royal Belgian Institute for Space Aeronomy, computer models show this radiation created a thick crust that goes down about 50 to 65 feet. This means the surface we're looking at now isn't the original material from whatever star system 3I Atlas came from. It's like a protective shell that formed during billions of years of space travel. The James Webb Space Telescope looked at this object back in August and found exactly that. The surface has been completely changed by radiation, not from our sun, but from space itself. This discovery is both exciting and frustrating for scientists. They were hoping that visitors like 3I Atlas would give us direct samples of what exists around other stars. Instead, we're looking at something that's been heavily modified by the journey itself. It's like trying to read a book that's been weathered by rain for thousands of years. The original text is still there, but it's covered by layers of damage. The only way we might see the original material is if the sun's heat during the closest approach burned off enough of that protective layer. That's what researchers are watching for now. They want to see if solar heating revealed what this object looked like when it first formed around another star billions of years ago. The brightness surge that defied physics. Here's where things get really weird. When 3I Atlas swung past the sun, instruments detected something that doesn't make sense. The object started putting out carbon compounds and water molecules at a rate 40 times higher than just a month earlier. It was like someone suddenly turned on a faucet, but comets don't work like that. Normal comets heat up gradually as they get closer to the sun, and they cool down gradually as they move away. They follow smooth, predictable curves that we can calculate ahead of time. But 3I Atlas spiked hard and fast, breaking all the rules we thought we knew about how these objects behave. Space observatories that can see objects near the sun, like SOHO, Stereo A, and GOES 1, all captured images during the closest approach. They could see the elongated shape and the glow, but there was something missing. Where was all the dust? When comets get close to the sun, they produce massive amounts of dust. That's what creates their spectacular tails and makes them visible from Earth. But 3I Atlas barely produced any dust at all. Some researchers think maybe carbon dioxide was acting like a protective shield earlier in the approach. Carbon dioxide turns to gas at much colder temperatures than water ice, so maybe it was keeping the surface cool. Then right around the closest approach to the sun, that layer burned off completely. Suddenly, the water ice underneath was hit with direct solar heating, causing the massive brightness surge. That explanation fits the physics we know, but it requires a very specific internal structure that we've never seen in comets from our own solar system. This suggests 3I Atlas formed under conditions that were completely different from anything in our neighborhood. The question is, what kind of star system creates objects with this weird, layered composition? Hidden secrets under a radiation-scarred surface. The James Webb Space Telescope gave us the most detailed look at 3I Atlas that we've ever had. Webb can analyze the molecular fingerprints of objects with incredible precision, and what it found creates even more questions. The radiation damage goes much deeper than anyone expected. For billions of years, high-energy particles from supernova explosions across the galaxy have been hitting 3I Atlas. These cosmic rays don't just hit the surface and bounce off. They penetrate deep into the object, going down dozens of feet and changing the molecular structure of everything they touch. Computer models suggest this has created a crust that's completely different from the original material. When we analyze the light coming from 3I Atlas, we're not seeing pristine samples from another star system. We're seeing a radiation-modified shell that formed during the journey through interstellar space. This is a huge problem for scientists who want to learn about other star systems. They were hoping interstellar visitors would be like messengers carrying information about planetary formation around different types of stars. Instead, it's like receiving a letter that's been through a shredder and then taped back together. The information is still there, but it's been scrambled beyond recognition. The only hope is that the sun's intense heat during the closest approach might have burned away enough of that modified crust to expose original material underneath. If that happened, the next few weeks of observations might reveal what 3I Atlas actually looked like when it first formed. But if the crust is too thick, we might never see through to the original composition. Unprecedented global response and defense protocol. On October 21st, something unprecedented happened. The International Asteroid Warning Network made an announcement that caught everyone's attention. They were starting a coordinated observation campaign targeting 3I Atlas, running from November 27th through January 27th, 2026. Now, IAWN does these campaigns regularly. They've done 8 of them since 2017, about 1 per year. They use them to practice coordinating global observations of asteroids that might pose collision risks to Earth. But they've never targeted an interstellar object before, not once. This is the first time in the history of the organization. The official explanation is technical. Comets are harder to measure precisely than asteroids because their fuzzy halos make it difficult to pinpoint exactly where the solid part is located. IAWN wants to practice these techniques on 3I Atlas because it's a good test case. That's a legitimate scientific reason, and it makes sense. But 3 weeks before this announcement, Professor Avi Loeb from Harvard submitted a white paper to the United Nations. The paper, written with researchers Omar Alidi and Gershon Tenenbaum, made a specific recommendation. The international community should coordinate observations of interstellar objects with maximum coverage, global cooperation, and comprehensive data sharing. The reason stated in that paper was direct. These objects could pose a threat to humanity if they happen to carry alien technology. The sequence of events is worth noting. White paper submitted September 30th. IAWN activation announced October 21st. First interstellar target ever chosen. At the same time, the European Space Agency's JUICE spacecraft has a unique opportunity. JUICE is on its way to study Jupiter's moons, but right now, it has a perfect viewing angle to observe 3I Atlas just after its closest approach to the Sun. The observation window opened November 2nd and runs through November 25th. JUICE is using every instrument it has: visible cameras, infrared detectors, particle sensors, all gathering data that no Earth-based telescope can match. On November 4th, JUICE makes its closest approach to the object at 64 million kilometers away. That's close enough to see structure and measure activity levels with incredible precision. But there's a catch. JUICE is so close to the Sun right now that it's using its main antenna as a heat shield. Data transmission is severely limited. Everything being collected during these critical observations won't be downloaded to Earth until February 2026. So we wait 3 months to see what JUICE discovered during the most important observation window we'll ever have. The acceleration mystery that changes everything. On October 29th, the Atacama Large Millimeter Array detected something that changes the entire story. 3I Atlas was not where pure gravitational calculations predicted it would be. The deviation was small but measurable and confirmed by multiple sources. This means the object is experiencing acceleration that can't be explained by gravity alone. NASA's Jet Propulsion Laboratory quantified this through their navigation engineer David Farnocchia. They found 2 components of acceleration, one pushing away from the Sun and another perpendicular to that direction. Both are measurable and both require explanation. The standard answer is outgassing. As ice on the surface turns to gas, it escapes and carries momentum with it. Newton's third law says the object experiences an equal and opposite force, like a natural rocket engine driven entirely by solar heating. This explanation works for normal comets, and it should work here too. But Professor Loeb ran the numbers, and they don't add up. If outgassing explains the measured acceleration, and if we assume reasonable gas velocities based on temperature, then 3I Atlas lost approximately 1/6 of its total mass during the closest approach to the Sun. That's roughly 5.5 billion tons of material ejected into space over just a few weeks. That's an enormous amount of material. If it really happened, there should be visible evidence everywhere. A massive cloud of gas surrounding the object, expanding outward, glowing from solar radiation, easily detectable by any telescope pointed in that direction. This gas cloud should be obvious in images and clearly visible in spectroscopic analysis. This sets up a critical test that will determine how we interpret everything else about 3I Atlas. Starting in mid-November, when the object emerges from the Sun's glare and becomes visible again from Earth, observers will be looking specifically for that gas cloud. If it's there, the natural explanation holds up. If it's not there, we have a serious problem. The December test that will decide everything. December 19th is marked on calendars around the world. That's when 3I Atlas makes its closest approach to Earth at 267 million kilometers away. On that date, hundreds of telescopes will be aimed at this single object. Professional observatories, space telescopes like Hubble and Webb, and amateur astronomers with good equipment will all be checking for the same thing. Is the gas cloud there? This isn't a complicated question, and it's not open to interpretation. Either there's a massive cloud of gas containing billions of tons of material, or there isn't. The math is clear. Natural outgassing at the level needed to explain the acceleration requires a gas cloud so large it would be impossible to miss. If December observations confirm that massive gas cloud, then 3I Atlas is a comet, unusual in composition, extreme in behavior, but ultimately explainable through known physics applied to an object from another stellar environment. Case closed, mystery solved, natural explanation confirmed. But if December observations fail to detect the expected gas cloud, then we have a fundamental problem. The acceleration is real. It happened. It's documented by multiple independent sources. And if outgassing didn't cause it, what did? Loeb stated this explicitly in his research. If no gas cloud is observed, the reported non-gravitational acceleration might be regarded as a technological signature of a propulsion system. This isn't wild speculation. This is the scientific method applied to unusual observation. We have a prediction, and we're going to test it. There's historical context that makes this test even more important. The first confirmed interstellar object, 1I Oumuamua, also showed non-gravitational acceleration when it left our solar system in 2017. Deep searches by the Spitzer Space Telescope found no gas and no dust that would indicate active outgassing. That's why some researchers proposed Oumuamua might be a tumbling light sail, thin and reflective, pushed by radiation pressure rather than gas jets. Most scientists disagreed with that interpretation, arguing there must be some form of outgassing that Spitzer couldn't detect. It's easier to imagine unusual but natural chemistry than to consider artificial origins. But now, we're seeing something similar with 3I Atlas, non-gravitational acceleration, and a clear test case where we can check for the expected gas cloud. If it's not there, the Oumuamua questions come back much stronger this time because we have better instruments and a clearer test. What this means for our understanding of the universe. We have exactly 3 confirmed interstellar visitors in our entire database: Oumuamua, 2I Borisov, and now 3I Atlas. That's not enough data to draw broad conclusions about what travels through the space between stars. That's barely enough to notice patterns. Oumuamua was weird, elongated shape, unexpected acceleration, no visible activity. 2I Borisov looked more like a normal comet with active gas production and predictable behavior. And 3I Atlas has explosive brightening, non-gravitational acceleration, and unusual spectral features that triggered the first ever IAWN targeting of an interstellar object. Maybe they're all natural. Maybe interstellar space is just more diverse than we expected. Different stellar environments could produce different types of objects. Different radiation fields could create different surface modifications. Different formation histories could lead to different internal structures. That explanation is reasonable and probably correct. But when Loeb asks for comprehensive data sharing and publishes papers about testing artificial origin theories, he's not being sensational. He's applying the scientific method to an unusual situation. He's saying we should test all reasonable possibilities, including ones that make us uncomfortable. Because here's the thing, nobody wants to say directly. If you were designing a probe to travel between star systems, to survive billions of years in interstellar space, and to remain dormant until approaching a star, what would it look like? It wouldn't look like a spaceship from science fiction. It would look exactly like a rock. It would be made of the same materials that naturally exist in space: ice, rock, carbon compound. It would need to blend in because there's no other way to protect it from radiation and impacts over such vast timescales. The journey itself would create a protective crust through radiation processing, and it would probably activate based on thermal thresholds, detecting radiation from a star and responding accordingly. That's not what 3I Atlas is, but the point is that distinguishing between a very unusual natural object and a designed object isn't simple when both would have similar surface properties after billions of years in space. This is why systematic testing matters. This is why the gas cloud observation in December is so critical. Right now, we're in the observation phase. JUICE is collecting data that we won't see until February. Amateur astronomers will start observing again around November 11th when 3I Atlas emerges from solar glare. The IAWN campaign kicks off November 25th with coordinated global tracking. December 19th is the big test for the gas cloud. January brings final observations before the object becomes too dim to study. Over these next few months, we'll accumulate more information about 3I Atlas than we have for any previous interstellar visitor. We'll answer questions and probably generate new ones. And we'll learn something fundamental about what travels through the space between stars. What makes this moment significant is that we're the first human generation with the technology to investigate these objects properly. Webb can analyze composition with incredible precision. The Atacama Array can measure positions down to tiny fractions. JUICE can observe from unique vantage points. Global networks can coordinate observations in ways that were impossible just a few years ago. 3I Atlas came from somewhere beyond our solar system. It traveled for billions of years through conditions we can barely imagine. It arrived here during the brief period when humanity has the technology to observe it thoroughly, and it's behaving in ways that challenge every model we've built based on objects from our own cosmic neighborhood. The visitor is here, the observations are ongoing, the tests are designed, and over the next few months, we're going to find out whether 3I Atlas is just a weird comet that challenges our understanding of natural processes, or something that makes us reconsider what we thought we knew about objects traveling through interstellar space. Thanks for watching another episode. While you are still here, make sure to click the video on your screen for more quality content.